Hi, this is ECE 313 Crash Course, and today we're talking about all the distributions of discrete random variables we talk about in the class. There are so many distributions, each with different significance, and it's confusing which ones to use, but today we're going to discuss them in an orderly fashion and their uses so you get a better understanding. First off, a quick review of the random variable. A random variable, often denoted x, is a variable that has probabilities of taking certain values in a sample space. It can be described in terms of probability mass function, or PMF, which is the probability that the random variable takes on a certain value, expectation or mean, or E of x, the summation of the values the random variable can take on multiplied by the probability that it will take on these values, and variance, or var(x), how spread out the PMF of x is, which can be also written as E bracket x squared minus the expectation squared. And the standard deviation is also the square root of variance. Now onto distributions of random variables. Let's say we have a coin and we flip it. There are two possible outcomes of the flip: heads, which is a success, or tails, which is a failure. To describe this situation, we say that random variable x has a Bernoulli distribution with parameter p equals 0.5. Bernoulli distribution is used to describe distributions with only two possible outcomes, and p is the probability of success. The PMF is as described, where I equals 1 is a success, and the expectation is p and the variance is p times 1 minus p. Now let's say we have a biased coin with 80% chance of getting heads. The distribution would be described as a Bernoulli with p equals 0.8. Easy, right? Now let's flip the coin a bunch of times and represent the probability of getting a certain number of heads with another distribution, the binomial distribution. If the coin is flipped n trials and we want to see k heads, with each head having probability p, the PMF is as shown. Breaking this down, p to the k is the probability of succeeding k times. 1 minus p to the n minus k is the probability of failing n minus k times, and n choose k is the number of these outcomes occurring. Let's say we flip our biased coin 10 times and we want to find the probability that we get 6 heads. Then the PMF is as shown. Now the expectation of this is equal to n times p, and the variance is equal to np times 1 minus p. Alright, what if we only wanted to count the number of trials until we see one head, one and done? Well, we can use a geometric distribution for this. If we reach the first head at the kth trial, we can write the probability of it happening as shown, with 1 minus p to the k minus 1 as the probability of failing every trial before the kth trial, and p being the one time we succeeded on the kth trial. Expectation is 1 over p, and variance is 1 minus p over p squared. If we flip our biased coin 3 times before reaching one head, then the PMF is as shown. One property that makes geometric distributions special is the memoryless property. Suppose you are calculating the probability of getting your first head after 5 or more flips, and you've already flipped your coin 3 times. The probability of this event is equivalent to the probability that you get your first head after 2 or more times. Essentially this, where in this case, I is 3 and j is 2. Geometric distributions forget about the first 3 coin flicks, as that does not affect the probability of getting heads in the future. Alright, we're in the home stretch now. The last distribution we discussed is the Poisson distribution. Sometimes we have situations where there's a very high chance of failure. We can denote this distribution, which is a binomial distribution with n approaching infinity and p approaching 0, as a Poisson distribution. Unlike the binomial distribution, we only have one parameter lambda, which is equal to np. The PMF is then represented as shown, and both the expectation and variance are lambda. Let's say, for example, you're calculating the probability that a team scores 3 goals in the World Cup game. when the average is 2.5 goals per game. You can use this Poisson distribution to find the exact probability. Now you know which team to bet on. Well, that wraps up the distributions of discrete random variables crash course. Thanks for watching.